Okay, so welcome to lecture number 6. So in this lecture, now we are going to start putting electrons in a crystal, and I will talk about Bloch's electron. So we are still building our base how to represent E versus K diagram. So if you recall that we just did last lecture, we did reciprocal lattices. Last two lectures we did reciprocal lattices. The idea was that, of course, that electron wave which had a small k in there, the wave vector, its dimension was in reciprocal space. Then we generated capital K vectors, those reciprocal lattice vectors, those were done with a purpose. Those vectors we are going to use to represent the band diagram, that is E versus K diagrams. So ultimately we are going to be using that, but still we are building towards it. So what I am going to do is, now remember, now I am going to start including the crystal underlying a. So far we did free electrons. So we started with free electrons. In free electrons, what we did, what are the things we did? Let us just think about it. Free electrons. When we did with free electrons, in this case, what we did was two things we did. First, we said all these electrons are non-interacting. Neither there was a ion electron interaction, nor there was electron interaction. Therefore, we did this V equal to 0 is first thing we did in our solving our Schrodinger equation, which was h square by 2m E. In this equation, we had substituted V equal to 0. We had made this go away. We had made this quantity equal to 0, and we have made this go away, and then we said this is a free electron, and we, what did we get? We got energy as equal to h square by 2 m E k dot k, or k square is what we got, right. That is what we had derived for a free electron energy. Now here comes the problem. Okay, fine. Saw that it does a improvement, it gives us some better results than Drude's theory, but then we also said there are many things free electron theory does not explain. It does not show why a material should be insulator, why a material should be semiconductor. It does not show, for example, why in aluminum the Hall coefficient should be of opposite sign than expected, etc., etc. There were failures of free electron theory which we discussed. So what do we need to do? We said that we will have to include these electrons. We will have to, what we have not done is that we have ignored the underlying lattice, its periodicity, etc. So what we are going to now do as improvement is we will solve the problem in two steps. In first step, what we are going to do is that we are going to keep relation between E and K simple. We will just use the result of free electron theory, that is E equal to h square 2 m E k small k dot small k, which is wave vector. And of course, in this case the solution we got was phi was of position was e to power minus j k dot r. That was the form of the solution we got for this. So, we will continue to use that as a solution in there. Okay. Now, so first step we are going to do that. Second step we will include the potential. We will include the potential which will or may be present. Now, what does that mean? Let us look at it. What does the potential mean? Where does the potential come from? Now, imagine V comes from what? It comes from, you can see there are many electrons. There are many electrons in the system. What kind of, let us divide the electrons. We think of valence electron, we can think of core electrons, we can think of nuclei. So, we are in a crystal we will have interactions between valence electrons, we will have interaction between all these entities, nuclei. So, and we have many electrons, all the electrons and all the ions, all the nuclei which are present in there in the system, all these are interacting with each other. Indeed, we can write a potential for it. So, if we were to solve for Schrodinger equation for it, then we will have the Hamiltonian will include sum of kinetic energy, I should say, energy for all these particles, sum of kinetic energy for all these particles apart from potential. That indeed would be a really formidable problem, and to date there is no way of solving such a problem. So, the approximation, first approximation we make is, we think of valence electron and ions, which means core electrons plus the nuclei. So, that all is buried, the core electrons get buried with nuclei and we call them ions. That is one thing first, but still we have huge number of valence electrons and we have huge number of ions. All of them are present. Still the Hamiltonian will include kinetic energies because of all these entities and again the potential. Essentially, then what is done is that this problem still remains formidable and impossible to solve with the present day computers. So, what can you do? One way is there are certain ingenious formulations made in which you consider a single electron problem, you reduce the whole problem to an equivalent problem which has a single electron in an effective potential. In an effective potential due to ions and all other valence electrons. Due to all other valence electrons. So, that is what we are going to have to all other valence electrons and ions will reduce that to an effective potential. There is ingenious formulation for it. So, that you treat this single electron, you solve a single electron Schrodinger equation in a effective potential. The exact solution of this problem is beyond the scope of this course. So, what we are going to be interested in is, we will assume what the results will come out of this, but what we are going to be interested in is that, notice, because our lattice is periodic, it is natural to assume potential is also periodic with same periodicity. Since the period in the lattice is capital R, therefore, potential at any position must be same as potential at any, should also have the periodicity of the lattice which is capital R. So, that should always be true. Now, what we are going to do is solve this whole problem in two parts. First, we are going to look at, in the first part which I am going to start now, is not really solve the problem. I am going to use that energy relationship is the same, E equal to h square by 2m k square. That means, whatever we got from free electron theory, let us keep the energy relationship same, and then what we are going to say is that what is the consequence of the fact that underlying potential is periodic, periodicity being shown here. So, if this is the periodicity, then what will be the consequence on how can we use that to represent the band diagram? That really, and energies we will use is the free electron energy, but using this idea of periodicity of lattice and therefore that of potential, how can you represent energy versus k diagram? That is really we want to do. So, let me try to explain one more time. So, energy we are going to assume as h square by 2m k dot k Now, you can already appreciate what the problem is. Problem is, my paper is two dimensional. So, if I want to choose, write this energy versus k diagram is what I want to make. Since k is a vector, so it has infinite possibilities, it could be pointing in any possible direction. Which direction should I represent here? Direction should be what? What vector should I take? That is my problem. And you see, we can pick only one particular direction. Let us say we pick only one direction called kx. For example, if we pick this kx direction, then that is only one Ek diagram. Such diagrams could be infinite number of diagrams, because I will have infinite number of diagrams I will have to plot to represent this E versus k. That obviously is not reasonable. So, what is the method by which I can represent Ek diagram is really what we are proceeding towards. So, what we are going to do is we are going to use the idea of the fact that underlying potential is periodic, meaning thereby V is equal to R plus R, and therefore use this to represent these energies in an ingenious way, in an interesting way. That would be the first step which I will do in today and one more lecture. Following that, only after that, what I am going to do is, then I am going to approximately show approximate solution for approximately assume what value V is. Right now, we are not interested in what V itself is. Just that today's lecture we are going to use the fact that it is periodic, that is all. But in subsequently we will use the approximate value of what Vr is, what the behavior of Vr is, use that to find an analytical solution. Using that, I will show you that because of presence of Vr and its value and its nature, how a band gap can emerge, and therefore material can become a semiconductor or insulator. Having done that, to understand conceptually, then of course we will we'll assume that there is some real potential, which we will not really do in this class, but there is real potential. Based on that, people have done the calculations of those band diagrams. So in the first step, we would have learned how to represent E versus k using energy, using this relationship right here, which is given here. Once you learn the representation, and second part we will assume a potential, and I will show you the consequence of potential. But then the real thing, I will show you then the Ek diagrams, what the Ek diagrams would look like if the potential were real. But that final one, calculation, will not be part of the course, because that is course by itself. So that is how I have given you an overview of next 3-4 lectures, how we are going to proceed. So at this point of time, let us assume these two things, that energy relationship is just this. So you need to represent this energy relationship. Second, E versus k diagram. Second thing is that my potential is periodic. That is what only result we are going to use right now, and see what the consequence of this is. All right. So you may wonder, then why did we do reciprocal lattice? Very soon you will see that. Just today you will see why did we do reciprocal lattice. They are special vectors, and they will do something for us, and that is what we are going to do. And one more thing we can write down here is solution for this is of form e to power j k dot r. All right, there is plane waves involved. So with this background, let us start this lecture, and we will start with what is called as Bloch's electron. So let us start with this, what is called Bloch's electron. What is this Bloch's electron? One that follows one electron. So maybe I should one electron Schrodinger equation in a periodic potential. Oh, hopefully you see the difference. In free electron, that was the only difference. In free electron, this potential was 0. Otherwise, that was also a one electron problem. So here also I am still dealing with one electron problem, and I have already shown you the ingenious ways by which real problem is reduced to a one electron problem. One electron problem where the interactions, the potential is really represented by interactions of all valence electrons, electron-electron interactions, and also electron and ion interactions. So all those are buried in one effective potential. So that part can be done. So we have one electron problem in a periodic potential of form Vr, and it has a periodicity of the direct lattice. our lattice periodicity is shown by R. Remember what is R? R of course is my primitive lattice vector defined by n1 ni ai summation, where I of course is 1, 2 and 3. So, in other words, I expanded form R is n1 a1 plus n2 a2 plus n3 a3, and this is the vector where n1, n2 and n3 are all integers. In this what happens? So, Bloch's theorem says that solution to such a problem, remember free electron solution was this was the free electron solution. Now, question is, if you solve one electron problem, Schrodinger equation in a periodic potential, whatever that potential is, we do not know what the potential is, just that it is periodic and has a periodicity of the direct lattice. Then if that is the case, then the solution of this equation is of form of e to power j k dot r, which we already knew in free electron, but also an additional term u k r. And what is this u k? This u k, all we know about this u k is that it is also periodic. So, Bloch's theorem says that whatever the solution, exact solution we are not interested in at this point of time, but that if the potential is periodic, then solution will be of this form where u k will be periodic. That is the Bloch's theorem. So, that is the solution we are going to use, and see nature of solution will be of this form. The fact that solution is of this form itself gives us a huge amount of information, and that is what we are about. This lecture will be about this part only. So, let us look at that. So, what happens to wave function? Happens to our wave function. Okay. And notice I am using a subscript k because this corresponds to some value of k. K can be, there are many k values, any k value will satisfy this Schrodinger equation. Real solution will be therefore summation of all those k values, and hence I am putting an index k for a k value. So, okay, with that let us write this solution. What will happen to phi k at r plus r? That is the question we are asking. Wave function at k, this we have derived in the previous equation. I have written it here, right here. This is what we have written here, and now what we are doing is we are asking what will this quantity will be equal to. Okay, this quantity, let us just substitute it in there. Therefore, so that we are going to write as e to power j k dot now r plus r and u of k, which will be r plus r. So, that is what this quantity will be equal to. I just substituted in there. So, now what happens? What does that mean? That means maybe we should keep labeling the equations also. Let us call this as equation number 1, let us call this as equation number 2, let us call this as equation number 3. So, now look at equation number 2. Equation number 2 says, so let us just write this down first. So, this quantity will be equal to e to power j small k capital R times what? E to power j small k dot small r, and now I am going to use equation number 2, which says, let us use equation number 2, which says u of k r plus r is same thing as u of k at r, that is periodic. So, I am going to use that. So, I am going to replace this by u k just r. Now, what is this quantity equal to? By equation 1, this quantity is equal to simply phi of r. This quantity is simply phi of r. So, therefore, phi of k r plus r is equal to e to power j k dot r phi of k at r, and all these are vectors, and that is just that is quantity. What does that mean? wave function in one primitive cell differs from another primitive cell by a quantity this, it differs by. So, there is a phase difference in wave function between, let us live with this equation, between one cell and another cell, there is a phase difference in the wave function. That is what we have figured out. But for special values of k, meaning for k equal to capital K, remember now here comes the reciprocal lattice vector. This special k, this special k is, remember, that is a reciprocal lattice vector. Now, for these values what will happen? If you substitute capital K for it, then phi of capital K r plus r will become equal to, if you substitute capital K in there, in this equation number 4, if you substitute capital K, then you remember the definition of reciprocal lattice itself was that e to power j capital K dot capital R was always 1. That is how it was chosen. Now, you can see why I chose it that way. In that case, phi of capital K would be equal, simply that, since that is equal to 1, therefore, this will happen. So, at lattice points, reciprocal lattice points, when small k, or sorry, not lattice points, at small k becomes capital K, for those vectors, in that case vectors which are pointing towards lattice cell versus another cell would be identical. All right. So, that is an important result. All right. Now, let us proceed further. Now, let us do a trick therefore. If this special capital K is a special vector, then if I have a small vector k, let me do this, let me do a little trick and express this as any small vector k, k prime, another capital plus a capital K vector. I can always split any vector into sum of two vectors, but just that I want to make sure that one of those vectors is capital K. So, if I take this small k to be like this, then what happens? Let us look at this. So, from 4, then from equation 4, what happens? Let us look at this. Phi of k r plus r will become equal to, let us substitute in there. So, that will become equal to e to power j k prime dot r e to power j capital K dot r since this quantity is equal to 1, therefore, phi of k r plus r, this will be equal to j k prime vector r phi of k r, and let us call this equation 5. Now, let us call this equation 6. Let us call this equation 6. Now, can you compare equation number 4 and equation number 6? Compare equation number 4 with equation number 6. What do you see? Something interesting, isn't it? Notice that they look the same. If you replace k by k prime, if you replace k by k prime, it makes no difference. It makes no difference, it remains the same. So, when you compare equations 4 and 6, if you compare equations 4 and 6, implies wave function has no unique k. That is, k and k prime same wave function. Unique k, but a set of k values which differ by capital K vector. Now, you can see why we did reciprocal lattice vector. Reciprocal lattice vectors are special. Remember, k was equal to k prime plus k. So, these two vectors differ by k prime and k vectors differ from each other by some k vectors, by a capital K vector. As long that is true, then the nature of wave function remains the same. Wave function does not change. That means, now that gives us a handle. That gives us a handle. So, now this conclusion which comes out of Bloch's electron from the fact that there is a single electron in periodic potential, we can now begin to use them for our purposes. So, what I am going to do is show you what it means, how does one reduce this problem. What I am now going to do is for sake of representation of EK diagram, make sure that K prime lies in first Brillouin zone. You follow that? What I am going to do is, since it does not matter what k you can choose, as long as if I have a small k vector, I can always find a small k, I can find a small k prime vector, which and these two vectors are different by a capital K vector, and it does not matter if I find this small k vector, wave function will remain the same. So, that is the logic I will use, and I will make sure that the vector I find, this k prime vector, always lies in the first Brillouin zone. And then instead of plotting E versus k diagram, I will plot E versus k prime diagram, and now since k prime is always in first Brillouin zone, therefore, the k axis does not need to go to infinity. Instead, it is only confined up to the boundary of the first Brillouin zone. You see, that is the first thing we want to do to limit our size of the band diagram. So, in order to do that, let me show you a little bit how we can do that. So, let us take this as an example. This is the same example which I had shown you for reciprocal lattice, where I was showing you Bragg's diffraction condition, construction of Brillouin zone. I had shown you construction of Brillouin zone in 2 dimension, and in 3 dimension is the same construction which you do. So, I am showing you again, going back to the same diagram which I had drawn in the previous lecture. In that direction, B1 and B2 were my lattice vectors, and therefore, this k was equal to m1 times B1 plus m2 times B2. In general, of course, k is equal to mi bi, where n summation is over I equal to 1, 2, 3. Right, 1, 2, 3 in general, but since this is a 2-dimensional problem which I am going to represent here, so k is just that, and this is the lattice which I have shown you. Blue line I had shown, construction I have shown you, that was the Brillouin zone. So, now what I am going to do is I want to show you that choose whatever k you want, will always represent, will find a k prime which lies in the first Brillouin zone. Let us do that. Let us take that as an example. All right. In order to do that, let us do it like this, that let me remain consistent with example I have chosen, so that the construction is easier. So, let us go somewhere here, let us go somewhere, for example, let us go somewhere here. Okay, let us go there somewhere here. Suppose this is my k vector. Suppose I choose a k vector which looks like this. Suppose I have a k vector which is like this. This is my k vector. This is my k vector. All right. If this is the k vector, I can always find a capital K vector which will reduce my k vector into the first Brillouin zone. Let me show you that as an example. So, what you do is you choose another capital K vector which is like this. Remember, capital K vectors are those vectors which which are drawn by, or I will use this, I will write it more explicitly here. So, this capital K vector then is equal to, let us choose the value of m 1 and m 2. So, it is 1 and 2. So, 2 b 1 plus this is 2 b 2. This is the capital K vector I have chosen. If so, then what is K prime vector? This is K prime vector. So, this is K prime vector. If this is K prime vector, if this is a K prime vector, I can represent the same K prime vector right here. Draw the same parallel vector from this origin, the origin must remain same. So, that is the K prime vector. Now, notice I will show you that it does not matter, this K prime is not unique vector. Many K vectors, many such K vectors lead to same K prime vector. This is what I want to show you from this diagram. It does not matter. This is the second conclusion I want to show you. First, I have shown you that if you give me this K vector, I will find you always, it is always possible by taking a neighborhood lattice point, that means capital K vector. It is always possible to reduce to another K prime which is within the first Brillouin zone. You can see this is within the Brillouin zone. Second statement I am making is that this K prime is not unique. This K prime is result of many different K's. It is possible that it is from many small K's, this K prime could be same, and that example I will show you now. So, for example, let us take it like this. Suppose you want to take somewhere here like this. Suppose this is your K vector, another K vector which is like this. This is your small K vector. So, in order to bring this into first Brillouin zone, let me choose this as my capital K vector. This is my capital K vector. This capital K vector you can see now is minus b 2 vector. This is just a minus b 2 vector. Remember, this is b 1 and this is b 2. This is b 2. This is b 2 and this is b 1. This is just minus b vector. So, therefore, what does it mean? This means that this is K prime vector. This is the K prime vector. All right. If that is the case, then you see this K prime vector is same as this red colored K prime vector I have shown, if I transform to origin. So, whether it is this K or whether this K, both lead to same K prime. Okay. So, now what are the conclusions we draw? Next page I am going to write down the conclusion which I draw from this. So, but let me say it in words right now one more, and I will repeat it again. So, as a consequence of periodic potential, Bloch's theorem said that first I told you that it is always possible, not always possible, it is possible to reduce a problem to one electron problem with an effective potential, number 1. Number 2, once I have one electron problem, then if one electron problem is being solved in a periodic potential, which is natural to assume, since the lattice has a periodicity. So, the potential should also have the same periodicity of R. If there is a periodic potential, then there is a Bloch's theorem which gives you the form of the solution. Given that form of Bloch's form of the solution, what we are able to tell is that wave function in one primitive cell to another primitive cell is different by only a phase, but for some special values of k, there is no phase difference. That is number 1. Number 2 conclusion we made was that there are many different values of small k's which will lead to the same wave function, We have used this as a consequence of Bloch's theorem. We have used this result to show that if you have, remember I started saying when I want to plot Ek diagram, I have infinite values of k possible. So, and infinite extent, of course, how far it can go, it can infinite extent. Now, since any k value which you have, I can always represent by a small k, I can represent by k prime vector which is within the first Brillouin zone. At least what we have achieved is that we have confined the infinite extent of this k vector within a narrow confine of a first Brillouin zone only. At least that much we are able to do. So, let me write down. So, and second thing I have shown you is there is no uniqueness, whatever k prime vector you find, this same k prime vector represents many different many infinite number of, not infinite, very large number of small k vectors, and I have shown you two examples. I have taken this as a, I have taken this k vector and I have taken this k vector, and I have shown to you that by using an appropriate capital K vector, reciprocal lattice vector, we can reduce it back to a small k prime vector, which are both are same, both and both are within the first Brillouin zone. That is the red line which I have shown you. So, that is a reciprocal lattice vector. So, let me write down the conclusion here. So, conclusion number 1, for a k value, it is always possible to find an equivalent k prime which differs from k by amount capital K only. It is always possible to find an equivalent k prime in first Brillouin zone. That is point number 1. I have a conclusion, but still energy is equal to h square by 2 m k dot k not h square by 2 m k prime dot k prime. It is not that. Energy is still, so x axis of Ek diagram, I can find a k prime, but the energy that I represent is still going to be real energy, which will be using k, not k prime. So, that is the one, that is the one point. The one point I want to make. Second, within this conclusion set 1 is that many k values can be represented by same k prime in first Brillouin zone. That is the conclusion I want to draw. All right. So, if these are the two conclusions, then now you can see, and now therefore, since at same k prime in first Brillouin zone, I can, this k vector, the small k vector represents, electron state. Remember, in free electron theory, we found that these are discrete and some states which electron can take. This k vector represents electron state, and this can be represented, and many these k states can be represented by same k prime within the Brillouin zone. So, question one asks is that in one Brillouin zone, therefore, how many, natural question to ask is how many electrons can I put? How many k states therefore are available only within the first Brillouin zone itself? In first Brillouin zone, how many k states are available? So, that is why next question, next logical question is, because k prime represents many k states, small k states, therefore, and this k prime is in first Brillouin zone, how many total number of states are there in the first Brillouin zone? That is the question we are trying to ask, and since once we know the number of states, then we know how many electrons we can put in the first Brillouin zone. All right. Next logical question is how many states in first Brillouin zone. That is the question we are about to answer now. All right. In order to do that, let me do this. Consider, and I just do a simple algebraic calculation. Consider a crystal of volume V, and you see a primitive cell has a volume V p is primitive cell volume, if n are the number of primitive cells, then clearly V is equal to n times V p. Now, assume that, remember, so if volume V is enclosed by vectors n1 a1, n2 a2 and n3 a3. So, think of this like this, that if n1 times in direction of a1, if n2 times in direction of a2, n3 times in direction of a3, that is the extent of my total volume. That means, so I take a in terms of primitive lattice vectors, if I take n1 steps in direction of a1, n2 steps in direction of a2, n3 steps in direction of a3, then I construct my whole volume. If that is so, then clearly n is equal to n1 multiplied by n2 times n3. So, n number, how many primitive cells are there therefore? So, if I took n1 steps in this direction, n2 steps in this direction and n3 steps in this direction, then total number of primitive cells which are defined by 1 a1 a2 a3 will be n1 into n2 into n3, then that many primitive cell, and I have said n is that number of primitive, total number of primitive cell in volume V. Therefore, this n must be equal to n1, n2 and n3. So, the whole extent of volume is determined by the multiples of a1, a2, a3, which are n1, n2 and n3. Now, remember, we apply again our good old this Born-1 Kármán boundary condition. We apply which was what you will recall in free electron theory. I had written phi of x comma y comma z being equal to phi of x plus L y comma z. You will recall I had written it something like this as a Born-1 Kármán boundary condition. Namely, there what goes in is like this: if something comes out of here, it basically has entered from that side. It has entered from the other side of the boundary. So, if this is the boundary, then it comes out, something comes out of here, but essentially enters from this side, as opposed to saying let us make the wave function 0 on both sides, so that it does not leak. In order to avoid the leak of wave function, confine the wave function in our material itself, what we had used was Born-1 Kármán boundary condition, a cyclic boundary condition which said, okay, we will not allow the wave function to leak out of material, but the way we will do it is that whatever is coming out of here goes back in from the other side. So, that is now I am going to write the same. So, now the material boundary is defined by the multiples of n1, n2, n3. So, we will use it in that context. So, I am going to write therefore, in that case phi of k at any position r will therefore be equal to phi of any position r plus n1 n I a I, where I could be equal to 1, 2 or 3, 1, 2 or 3, not summation, 1, 2 or 3. So, it is like this: if you, where is my boundary in this direction? After n1, this is the a1 direction. So, after n1 times I have my boundary here, that is why I have written n1 multiplied by a1, or if it is in direction of a2, it is n2 times a2 is where I encounter my boundary. So, I have written it like that in general form, where I is this quantity. So, now by Bloch's theorem what happens? By Bloch's theorem, what happens by Bloch's theorem? Phi of k of r plus this n I a I, this is vector a I, whatever n I as you know is 1, 2 or 3, and you apply sequentially to 1, 2 or 3. This at the period is equal to e to power j times, now I am going to write this as n I k dot a I. I am going to write it like this now, phi of k at r. Remember, where did this come from? This whole stuff comes from phi of r plus r being equal to e to power j k dot r times phi of r. That was Bloch's theorem solution. So, that is what I have applied here essentially. Okay, what does that mean? This implies you substitute in there. So, what does that mean? And since this quantity should be equal to, remember, use this equation here, since this quantity should be equal to phi of r, implies that e to power j n I k dot a I should be equal to 1. That is what it implies. So, if since a I is real, it is a direct lattice vector, it is a lattice vector. So, it is a real quantity, and if it is a real quantity, then dot product. So, then that means k must also be real, otherwise I would have gotten an imaginary, implies that k must also be real. If k was not real, then I would have got an imaginary component also. So, therefore, this implies that k is also real. All right. So, what I am going to do is, therefore, since k belongs to reciprocal lattice, since k, not reciprocal lattice, k belongs to reciprocal space, I am just going to express this k vector also as some multiples of L1 times B1 plus L2 times B2 plus L3 times B3, and these are reciprocal lattice vectors, where L1, L2, L3 need not be integers. Because if they were integers, then the small k will look like a capital K vector. So, just I am trying to do this, let us express, we have B1, B2, B3. So, let us express k as some multiple, some coefficient of that L1, L2 and L3 we are going to choose and use that, all right, which I am going to succinctly write as summation over Li and Bi. So, that you get the idea that I is 1, 2 and 3, all right. Okay. So, all these are not necessarily integer. Now, since we have we have that exponential, so now let us substitute this k, since we, let us go back to our equation here, that let us go back to this equation here, we substitute in here e to power j n I k dot a I. So, we will use this e to power j, let us see this j n I k dot a I. Okay, so, let us substitute in there. So, what do we get here? So, what we get is e to power j n I, for k we substitute L1 B1 plus L2 B2 plus L3 B3 dot a I equal to 1. What does that mean? Remember, whatever I value is, I 1, 2, 3, then you will pick only that L1 or L2 or L3 according to that in the dot product. So, that therefore, e to power j n I L I is what will get picked out of this, and B I dot a I will lead to 2 pi. So, I should put it 2 pi, that should be equal to 1. That dot product of a I and B I is simply 2 pi. You can see our definition of B I's, the reciprocal lattice vectors. This implies that n I into L I should be an integer, this quantity should be an integer, and let us give it a name. Let us give it a name of let us say, let us call it Q I. Let us give it a name of Q I. All right, this is an integer. So, this quantity should be integer quantity. What does that mean? That means k vector should be equal to 1 by n1. I am going to substitute in here. From here, I am going to write k as L1, which Q1 times B1 divided by 1 by n1 plus a integer quantity Q2 times B2 divided by 1 by n2 plus 1 by n3 Q3 times B3. Now, what is the volume enclosed by this k state? What is the volume as a consequence of this state? Remember, a vector k which is due to B1 plus B2 plus B 3 in the primitive cell leads to a primitive cell volume. This primitive cell volume will be equal to just B 1 dot B 2 cross B 3. It will be just this quantity, that is the volume of the primitive cell in the reciprocal space. Similarly, if you look at this K, what will be the volume occupied by this K state, and this quantity of course will be equal to, you can see, 2 pi whole cube divided by V p, that you can carry out this exercise. All right. Likewise, in reciprocal space, imagine equivalent to that, you think like this, these are integers, these are integer quantities, these are integer quantities. So, similarly, I am going to write what is the volume occupied by this K state, which is defined by 1 by n 1 B 1 plus 1 by n 2 B 2 plus 1 by n 3 B 3. What is the volume occupied by this? This is a one K state occupies this small k volume, which will now in this case will simply be, if I substitute in there, then instead of B 1 I will substitute B 1 by n 1, instead of B 2 I will substitute B 2 by n 2, and therefore and B 3 by n 3 I will substitute. If I do that substitution, then I will get this as 2 pi whole cube divided by V p divided by 1 by n 1, n 2 and n 3, which is equal to 2 pi whole cube V p times 1 by n. That implies that volume of primitive cell should be equal to volume associated n times what is the volume associated with a K state. And what is the implication of this? Implication of this I will write in next page and finish the lecture here, that since V k is independent of how the primitive cell was chosen. So, this result must be true as a general case. So, that means I should have, that means we should, this equation therefore says, since this is the volume associated with one K state in first Brillouin, and this is the total, this is the volume of the primitive cell, then that means I should have, and Brillouin zone represents a that means a primitive cell in the volume of the Brillouin zone, that means primitive cell in reciprocal space is really the Brillouin zone. So, therefore, this is the volume of the Brillouin zone. So, this is the volume of the Brillouin zone, this is the volume associated with one K state, that means I should have n K states in the first Brillouin zone. We must have n K states on which I can put in first Brillouin zone. This is where I am about to end my lecture. I have shown you now, that means if you had n primitive cells in the real lattice, in the real material which is given to you, if you had n primitive cells, then you have n K states available in the first Brillouin zone. So, you know how many electrons you can put in that, how many first Brillouin zone will contain how many electrons. So, this is something in conclusion we have drawn. We will use these two facts to now draw out our EK diagram. So, from the next lecture on, what I am going to do is, I am going to first show you how EK diagram could be drawn for a hypothetical one dimensional system. Then what I will do is, then I will take it for metals and I will show you how EK diagram is to be drawn for 3-dimensional system, for say aluminum or copper or some material like that, and from that point you will start appreciating what EK diagram is, and after that we will introduce actual potential and see how the band gap originates. Thank you.